All right, let's dive in. Today, we're cracking open the cookbook of artificial intelligence. We're going to find the fundamental recipe for how a machine actually learns. And you'll see it's not about crazy complicated code, but a few core, really elegant ideas that make the whole thing possible.
So let's kick things off with the one question that's at the heart of all machine learning. How does a machine actually get smarter? How does it go from making these wild, random guesses to giving us answers that are surprisingly accurate? Well, it all comes down to learning from its mistakes. But what does that really mean for a machine?
To get our heads around this, we're going to use a pretty simple metaphor. I want you to think of a neural network like a chef who's trying to perfect a brand new dish. To pull this off, our chef needs three key things. First, a way to taste the food to know if it's any good. Second, the right magic ingredients that give the dish its unique flavor. And third, you gotta have the perfect oven temperature to even start cooking. You get those three things right, and you are well on your way to a masterpiece. Okay, so let's start with part one, the taste test. Before any chef can fix a dish, they have to know what's wrong with it, right? Is it too salty? Too bland? In the world of machine learning, this is all about finding a way to precisely measure your mistakes.
The fancy name for this is a loss function, but it's a really simple, powerful idea. It just takes what the model predicted, compares it to the actual right answer, and then spits out a single number that tells you how wrong you were. A high number, that means the dish tastes terrible. A low number means we're getting close. The entire goal of learning is just to tweak the recipe over and over to get that loss number as tiny as possible.
But here's the thing. There isn't just one way to taste. If you're predicting numbers, like, say, the price of a house, you've got two common methods. L2 loss squares the difference, so it really, really punishes big mistakes. The downside? A single weird data point, an outlier, can totally throw it off. L1 loss, on the other hand, just takes the absolute difference. That makes it way more robust to those outliers, but it's a little trickier to work with mathematically. It's a classic trade-off. Do you want sensitivity or do you want stability? That's all great for numbers, but what if our recipe is supposed to look at a picture and decide if it's a cat, a chair, or a car? You can't just subtract cat from car. That doesn't make any sense. We need a totally different kind of taste test when we're dealing with categories. The most popular choice here is called cross-entropy loss. And yeah, it sounds complicated, but the idea behind it is actually beautiful. First, the model just gives a raw score to every possible category. Then we do a little math to turn those raw scores into probabilities that all add up to 1. So you get something like, okay, 87% chance it's a cat, 13% it's a chair, 0% it's a car. Then the loss is just based on how much probability the model gave to the right answer. If it gives the true class a high probability, the loss is low. If it gave it a low one, the loss is high. It's as simple as that. And this table, oh man, this shows a subtle but incredibly important difference with another method, hinge loss. Just look at Model 1 and Model 3. Hinge loss gives them both a big fat 0 for their loss score. It's basically satisfied. It's like, good enough, as long as the correct score is higher than the others. But cross-entropy? It sees a huge difference. It gives Model 3 a near 0 loss because it's super confident. Here's the key. Cross-entropy is never really satisfied. It's a perfectionist. It always pushes the model to become even more confident in the right answer. Okay, so we've got our taste test down. Now, for the second part of our recipe, the magic ingredient. This is the thing that gives a neural network its real power, what lets it learn these incredibly complex patterns that go way beyond simple straight lines.
This ingredient is the activation function. You can think of it like a little decision maker, a gatekeeper, inside every single neuron. After a neuron adds up all of its inputs, the activation function decides, is this signal important enough to pass on to the next layer? And by making this simple on or off kind of decision, it introduces something called nonlinearity. And that right there is the whole secret sauce. It's what lets the network bend and twist and warp its understanding to fit all the messy, complex patterns of the real world. These functions have really evolved over time. The original sigmoid was a good start, but it had a huge problem. At the very high and low ends, its slope just flattens out. That means learning grinds to a complete halt. We call that saturation. TANH was a bit better because its output was centered at 0, which helps with the learning dynamics, but it's still saturated. Then came ReLU, the rectified linear unit. It's so simple. If the input is negative, the output is 0. If it's positive, the output is just the input. But it's fast, and it doesn't saturate on the positive side, and that was a massive breakthrough. So after all that history, what's the bottom line for you? It's simple. ReLU is the standard. It's the go-to choice for this magic ingredient. If you're building a network today, you start with ReLU. You pretty much only try something else if you have a very specific, weird reason to.
All right, we have our taste test and our magic ingredient. Now for the final piece of our recipe, preheating the oven. And it turns out that how you start the learning process is every bit as critical as the process itself. A bad start can completely doom the dish right from the get-go.
So in our cooking analogy, this is all about the starting temperature of the oven. For a neural network, this is the initial values of its parameters, which we call weights. These are the little knobs the network is going to turn and tweak during learning. And where you set those knobs at the very beginning, well, it matters a lot.
So, what happens if the oven is too cold? What if we start all the weights with these teeny tiny random numbers? Well, you can see it right here. The signal going through the network just gets smaller and smaller and smaller with each layer until it basically disappears. The activations all just collapse to zero. And if there's no signal, there's nothing to learn from. This is the infamous vanish ingredient problem. And what if the oven is way too hot? What if we start with really big weights? Well, the exact opposite disaster happens. The signals get so huge that they push our activation functions, like TANH, right into those flat, saturated zones. Look at how all the values are just slammed up against the edges at -1 and 1. And just like before, if the slope is 0, the gradient is 0, and learning is dead in the water. So we need that just right temperature. And the solution is a really clever technique called Xavier initialization. The math behind it is all about one simple goal. Set the initial weights so that the variance, which is basically the spread of the data, stays the same as the signal passes from one layer to the next. It keeps the signal from either vanishing or exploding.
And the result is exactly what we want to see. With Xavier initialization, that distribution of activation values stays nice and healthy and consistent, layer after layer. It's not too hot, not too cold. It is the perfect Goldilocks zone that allows information to flow and lets the network actually learn something.
And just a final little note here. Remember our magic ingredient, ReLU? Well, since it literally just chops off all the negative numbers and sets them to 0, it kind of messes with the math a bit. So researchers came up with a small tweak on Xavier, often called chiming initialization, that accounts for this. It makes sure we still get that healthy gradient flow, even when we're using ReLU.
So there you have it. That is the basic recipe for intelligence. First, you need a taste test, a loss function to measure how wrong you are. Second, you need a magic ingredient, an activation function, usually ReLU, so you can learn complex stuff. And third, you have to preheat the oven with the right weight initialization so learning can actually get off the ground. These three things right here are the foundation that almost all of modern AI is built on.
Which leaves us with one final thought. We've just gone through the fundamental ingredients for teaching a machine. So, if you had this recipe in your hands, what incredible, challenging, or maybe beautiful masterpiece would you teach a machine to create? Something to think about. Thanks for joining us.